This lecture is about the frequency domain analysis of linear systems. The frequency domain analysis of linear systems is a very powerful tool to evaluate the performance of linear systems without ever computing closed form solutions in a time domain. It carries some of the most fundamental concepts in system analysis, including body plots, including gain and phase margins, and which come from gain and phase respectively. It is very useful to analyze systems that offer a interesting oscillatory characteristics, such as suspension systems and the like. So the topic is again frequency domain analysis. And we will also see some very concrete examples of the frequency response of mechanical and possibly electrical systems. But let me begin with some theory. So we are, in general, interested in the following element. We have an input, we have a transfer function, and we have an output. U is the input, Y is the output, and we have Y hat over U hat is equal to H of S. Now, the question arises as to what happens when U is equal to something like either sine omega t with some possible amplitude, or U is equal to cosine omega t with some amplitude too, or in general U is complex and U is equal to e to the j times omega t, again with some amplitude. The answer to this question we have already dealt with a few weeks ago. However, let me repeat it for convenience and because it truly belongs to this part of AE 3515. What we are interested in is therefore trying to understand, for example, what happens when our system initializes at 0 and then undergoes the following. Y hat is equal to H of S times the Laplace transform of U. Okay. Oh, I should add that when t is less than 0, we assume U is equal to 0. Okay. So is identically equal to 0, which is, for your information, summarized by these three parallel bars. I mean, they're supposed to be parallel. So, in order to get the response to the system in the frequency domain, what we need to do is apply first the Laplace transform of U. Okay. This Laplace transform is mostly well understood in this context. And if we understand it in this context, we will understand it in that context, because if U is a times cosine omega t plus j times sine omega t, we know that the answer y will be the response of the system, which will be h star u, okay, the convolution of the impulse response with u, okay, and it will be something like a of t plus j times b of t. Assuming a is real, which will not be always the case, then I know that a of t will correspond to the response to the cosine part of the signal, the input signal, and b of t will be the response due to the imaginary part of the output signal. Okay, so this will lead us to that, this will lead us to that, therefore computing directly the answer to this input will actually give us the response of the system to this input and that input, but this one is infinitely more convenient to use. So let's go through that. And since u is equal to a to the j omega t, we know that u hat, which is L of u, the Laplace transform of u, will be a times 1, my mistake, 1 over s minus j omega. Okay, we know that from the standard table, so that we know that for this kind of input, the output will be h of s times a times 1 over s minus j omega. Okay, that is the Laplace transform of the response y. All right, so from there on, we could and we need to go on, okay, and understand what the response y is. And for that purpose, what we will do is we will say that this will be, well, we need to decompose this thing, okay? And there are several ways of doing so, okay? And I will just seek a particular formula, which was I will try and see if I can write this as two terms, okay? C plus plus d over s minus j omega, okay? Where c and d are terms that I don't know about yet. All right, so so for that, I'm going to now erase the parts of these pictures I do not need, and in this case, I can erase all this, I can erase all this, I can certainly erase all this, and we will keep the rest, okay? Okay, so we have made room. And what I will do is I will say, well, here's what they need to look like. Okay, let me get my pen again. So I'm going to have C times S minus J omega plus D divided by S minus J omega must be equal to H of S multiplied by A divided by S minus J omega. Okay, so I know that C times S minus j omega plus D must be equal to A times H of S. Okay. Now, neither A nor H really depend on omega. Okay, and so we need to do a few more calculations.